Hello, my name is Zita Martins. I'm an associate professor at Instituto Superior Técnico in Portugal, and today I'm going to talk about the exogenous delivery of organic matter in the solar system by comets and primitive carbonaceous meteorites. So the solar system was formed roughly 4.6 billion years ago with the collapse of a dense cloud of interstellar gas and dust, which served as the building blocks of the future asteroids and comets. The organic matter from this initial molecular cloud may have indeed survived the protosolar disk phase, later being incorporated into planetesimals and experience alteration on the parent body of carbonaceous meteorites and comets. This is really what I'm going to talk about. It's about all this organic matter that was formed outside of the Earth and may have been delivered to the primitive Earth. So this organic matter may have been formed from UV radiation and thermal processing of interstellar ice grains, which were then accreted into the parent bodies of comets and asteroids, and then further processed, for example, with aqueous alteration process. And we believe that this influenced the distribution and relative abundance of the organic matter. There are a few studies on this. I'm mentioning here a few articles, and throughout my talk, I'll talk more about this. So here in this slide, we're just seeing the contribution of endogenous synthesis versus exogenous delivery. We know that the basic unit of life is made up of organic molecules, the building blocks of life. And those organic molecules may have been formed by two different sources. They may have been formed here on the Earth by endogenous synthesis, for example, on hydrothermal vents, or they may have been synthesized outside of the Earth and then delivered by exogenous delivery. And this exogenous delivery may have occurred by comets, interplanetary dust particles, asteroids, meteorites. So I will talk a little bit more about this in this talk. Why do we care so much about the exogenous delivery? Well, because this may have played a key role on the origin of life on Earth. So we know that since the Earth was formed until roughly 3.8 billion years ago, the Earth witnessed heavy bombardment by comets, meteorites, etc. And so we will see in this talk that those bodies, the comets and the meteorites, they are very rich in organic matter, and all those and the organic matter was brought to the Earth. And the timing, the geological timescales are important, because if the bombardment occurred until 3.8 billion years ago, we know more or less that life originated a little bit after that, roughly 3.8 billion years ago. There's lots of discussion in the scientific community about the exact dates that life originated on Earth. Some people say that it occurred much early, and because of the heavy bombardment, life was destroyed, and what we're seeing is a second Genesis. Some people say that no, that life originated much later, around 3.8. So there's ongoing discussion about that. But in terms of geological timescales, it's perfect. We have the bombardment by comets and asteroids. We have those comets and asteroids bringing the building blocks of life to the Earth. And then we have life originated after that. And indeed, we know that the exogenous delivery of organic matter by these objects, some of them from the asteroid belt, as we'll see, so the meteorites come from the asteroid belt, they may have contributed to the early Earth inventory and providing the first building blocks of life. And we'll talk a little bit about meteorites exactly because of that in a few slides time, because they may have provided the important clues that we needed to know about the chemical processes that occur on the early solar system and played a key role in the origin of life on Earth and perhaps in other planets of our solar system. So let's talk a little bit about that. So there was a paper by Chuba and Sagan from 1992, so not very up to date, but still a very nice paper that indicated the contribution of organic matter delivered exogenously throughout the time from 4.4 billion years ago until 3.0. And they did those calculations for IDPs, comet impacts, and meteorites. So on this talk, I'll focus mainly on meteorites and also on comets. Meteorites, let's start by meteorites. So the asteroid belt is located between Mars and Jupiter, and the asteroids are the parent body of most meteorites, not all, but most meteorites. There are exceptions. There are the exception of lunar and Martian meteorites. But for the rest, the asteroid belt is the source of most meteorites we have. So we may analyze meteorites in our laboratory, or we may prepare space missions to the asteroid belt and to different types of asteroids. Here I'm showing you an image of the Ryugu asteroid, which was taken by the Abusa 2 mission. This is a mission from the JAXA, so the Japanese Space Agency. And this is a very interesting space mission that already collected samples from this Ryugu asteroid. And later this year in December, fingers crossed, we will have samples arriving on the Earth, being sent to laboratories and being analyzed. So we're waiting on this mission with big expectation. This week, also a very special week, because we'll have the touchdown and collecting of samples from this asteroid, the Bennu asteroid. This is a NASA space mission, the OSIRIS-REx spacecraft, and we're all waiting for this mission to touch down and collect the samples and later on analyze the organic content of those samples. So it's a waiting game, and we're also expecting really nice results and more information, crucial information about this very primitive objects that will tell us about the chemical reactions that occur on the early solar system and about the contribution of asteroids for the origin of life on Earth. So when we're not having missions to asteroids, we also analyze meteorites in the laboratory. Meteorites have different compositions. We have the iron meteorite, we have stony irons, we have different types of meteorites. The ones I'm particularly interested in when we're talking about this issue of exogenous delivery of organic matter is actually the carbonaceous meteorites. They are extremely rich in organic matter, as we'll see, and they will provide very important clues about the organic matter that was delivered to the early Earth. But not only that, meteorites are also important because they delivered water to the primitive Earth. So I'm showing you here a plot that was published by Altvag et al. In 2014. And here it is plotted the deuterium over hydrogen ratio of water in different celestial bodies. We'll see here on the left-hand side in blue the Earth, the D over H ratio of water for the Earth. It has this value. And then we see plotted on the right-hand side the D over H ratio of water for different comets. Comets that exist on some of them on the Oort cloud, the strong dark pink. We see the values for comets from the Jupiter family. And then we see the values for the 67P comet. So all of them, as you can see, the D over H ratio has a much higher value, a different value. It doesn't fit the value of the D over H ratio of the water. So this was puzzling. But then scientists decided to analyze the D over H ratio of asteroids, and they did that by analyzing different carbonaceous meteorites. And they could see that actually plotted beautifully on the line of the Earth. So this gives us a good indication that the asteroids contributed significantly to the water that we have in our planet. Obviously, more studies are needed and more missions to comets are needed, but this is a good indication of the contribution of asteroids and later on of meteorites to the water we have here on Earth. Meteorites, and in particular carbonaceous meteorites, are very rich in organic matter. They contain 3 to 5% weight total of organic carbon, and this organic carbon can be divided, it is divided in two different fractions. The majority, which contributes with more than 70%, it's insoluble macromolecular material. This means that you can use as many different solvents as you want, that you can't extract that molecular material from the meteorite. That material is composed mainly of aromatic hydrocarbons in a structure that you can see a drawing here. This is from a paper from Pendleton and Alamandola from 2002. All the remaining less than 30% is solvent-soluble organic matter. So we use different solvents and you may extract different organic molecules. And so this table summarizes the soluble organic compounds that are present in the Murchison meteorite. We can see that there is a rich organic inventory that includes amino acids, carboxylic acids, purines, pyrimidines, amines, alkyl, aldehydes, ketones, and so on. An extensive list of organic molecules that are present. This is just for the Murchison meteorite that has been extensively studied throughout the years. But obviously, scientists have been studying different meteorites, different carbonaceous chondrites. And what we see is that the organic matter varies a lot within different carbonaceous meteorites. And I'll talk about that in a few slides time and try to understand why we have those difference of organic distribution. So I've been talking about organic molecules, but one of the questions we always have is, are we sure that the organic molecules that we detect in carbonaceous meteorites are really indigenous to the meteorite? Meaning, are they really extraterrestrial and not simple contamination from my hands or from the extraction procedure? Well, there are 4 ways to actually be sure that the organic molecules we detect in carbonaceous meteorites are extraterrestrial. The first one is detect organic molecules that are unusual in the terrestrial environment. As an example, we detect alpha-IB, isovaline, beta-ABA, beta-IB. Those are all amino acids that are present in carbonaceous chondrites, and they are unusual in the terrestrial environment. Way number 2 to be sure that what we're seeing is extraterrestrial matter is to compare the absolute abundances of the organic molecules in the meteorites to the levels found in the fall environment. So lately what we've been doing is actually to collect meteorites, and whenever possible also collect samples from the fall environment. So if the meteorites are from Antarctica, for example, we tried also to collect ice from Antarctica, very close surrounding the meteorites. And in fact, colleagues have been doing that. They found trace levels of aspartic acid, serine, glycine, and alanine, only one ppb, and no isovaline, beta-ABA, or beta-AB above the detection limits in the Allan Hills region of the Antarctic ices. So there are a few papers on that. Way number 3 is determination of enantiomeric ratios. So, for example, for amino acids, we see that in some cases there is nearly racemic, meaning a D/L close to 1 for pristine meteorites. What does this mean? Let me talk a little bit more about this. So we know that on Earth, living organisms, most cases, there are exceptions, but most living organisms use L amino acids. Imagine you have your hands. They are the mirror image of each other, but you can't superimpose them. It's the same thing with the amino acids. They exist on the L and D form, and most living organisms use L-amino acids. You can apply this, for example, also for sugars. Most living organisms use D sugars. So on Earth, over long periods of time, amino acids from dead organisms will be converted into the D form, still with the L excess, but they start to be converted from the L to D form in a process of racemization. This is what happens on Earth. So this gives you the tools to actually look to a sample and actually say if an organism is alive or if an organism is not alive anymore, and you can see this D over L ratio. For non-biological origin, such as in carbonaceous meteorites, the story is completely different. Not only we detect more than 80 different amino acids, and there's lots of review papers and book chapters on this, and I'm giving a few of them on here, but we also see racemic mixtures for most amino acids, which is in contrast with what we see on living organisms. But there is an exception. The non-proteic amino acid the non-proteic amino acid isovalene shows an excess of around 50% in the Murchison meteorite. This has been studied throughout the years, and actually the scientific community is debating on why we see this happening on meteorites, this excess of isovalene, of L-isovalene. The reason, well, it's a big question mark. Some scientists say it's due to the UV circular polarized light in the pre-solar cloud, and there are an extensive list of papers that have been published about this. And some other scientists say it's due to the solid solution phase behavior. That is, it forms conglomerate in enantiopore solids during crystallization, and so this is the reason. I put 3 dots here because it's not very clear why. There is not definitive answer, and so it is still under discussion. On this topic, I'd like to develop a little bit more. So I've mentioned before that alterations on the parent body of meteorites, so on the asteroids, namely aqueous alteration, may have contributed to this different distribution of organic matter. And in fact, we've published a paper in 2018 that showed that that the aqueous alteration may have played a key role on the distribution of organic matter. So on this plot, we show on the left-hand side a meteorite called Paris, which to date is one of the least aqueously altered carbonaceous chondrites we have access to. And then as we move towards the right-hand side, we have increasing aqueous alteration. This is according to the hydrothermal scale designed by Ruben et al. 2007 and Browning et al. 1996. And determined by Alexander et al. 2013. So we on the epsilon axis, we've placed the relative amino acid abundance of beta-alanine, and indeed we see as aqueous alteration increases, we also see an increase of beta-alanine in the carbonaceous meteorites. So this gives us an indication that aqueous alteration actually played a role on the distribution of amino acids, in particular for beta amino acids. Obviously, we need more studies, but this is a key step towards understanding the place and the role of aqueous alteration. Coming back to this, so I was telling you about the 4 different points that give us clues to be sure that what we are analyzing is actually an extraterrestrial molecule in meteorites. So the last point is to measure the compound-specific carbon or nitrogen or hydrogen isotopic compositions. So putting this in a plot, if we placed the delta deuterium versus the delta carbon-13, For terrestrial organic matter and also for the organic matter existing on the Murchison meteorite, we can see that the terrestrial organic matter is placed on the bottom left-hand side, meaning it's rich in hydrogen and is rich in carbon-12, so the light forms of hydrogen and carbon respectively. And on the top corner of this plot, we see the extraterrestrial organic matter that is enriched in deuterium and is enriched in carbon-13. I've also placed here uracil and xanthine, a paper that we published in 2008, and it shows that those two nucleobases are enriched indeed in carbon-13. I've talked about now for the last few minutes, I've talked about meteorites and asteroids, but not only asteroids and meteorites have visited us throughout history, but comets have also visited. You can see here a tapestry from the 11th century, and here on the top we see Comet Halley. It's if you look closely, this is a comet and not the sun. So this shows us that throughout history, comets have visited. And it's interesting because comets have also lots of extraterrestrial organic molecules that have been detected using telescopes, but we can also have space missions to comets. An example is a mission to Comet Ville-2 that showed that this comet had glycines. So the smallest of the amino acids was detected in this comet. Later on, the European Space Agency had a mission, the Rosetta Space Mission, to Comet 67P, Churyumov-Gerasimenko, and it was showed that this comet had carbon species. It was very rich in carbon species, including alcohol, carbonyl amines, nitrilyamides, isocyanates, etc. And it also had the polymer of polyoxymethylene. Phosphorus and glycine was also later detected in this comet, and lots of species. So indeed, Catherine Altweg, the PI of the Rosina instrument, indicated that the perfume of 67P is quite strong, with the odor of rotten eggs due to the presence of hydrogen sulfide, or stable due to the ammonia, and the pungent suffocating odor of formaldehyde. This is mixed with a faint bitter almond-like aroma of hydrogen cyanide. Add some whiff of alcohol, methanol, to this mixture, pair with the vinegar-like aroma of sulfur dioxide and a hint of the sweet aromatic scent of carbon disulfide, and you arrive at the perfume of our comet. So definitely a comet that doesn't smell nice. Obviously, we've had a few past missions, as I showed you, comets, but I always like to look forward, and I'd like to indicate to you a future mission to a very pristine comet. It's a space mission called Comet Interceptor. It was just selected last year by the European Space Agency, and this will be a mission that will be launched in 2028, according to the schedule. And this will analyze for the first time a very pristine comet that will enter for the first time in the inner solar system. So we hope to analyze a comet that has never been significantly been altered by entering the inner solar system. So this will be a first, and it will provide us with very important information about the comet, about its organic matter and composition. So we wait for this space mission. But comets also had a role to play. So in the past, we know that the impact of comets may have also played a key role in generating more organic matter. And one of the suspicions was that, as we know that organic matter exists in comets, their impact would generate enough energy to process that organic matter and to generate more and more complex organic molecules. So in order to test that, our group actually used the impact gas gun of the University of Kent. They contacted us to analyze their experiment, and so we started a collaboration a few years ago. All this started by an ab initio molecular dynamics simulation from our colleague Neil Goldman in 2010 that showed that shock waves passing into comets would yield amino acids. And so the colleagues from the University of Kent had the idea of actually testing this with in their laboratory in the University of Kent, and then they contacted us. Their idea was that amino acid precursors such as ammonia, methanol, and carbonyl compounds were observed in comets, and they believed that the impact would generate enough energy to generate amino acids. And so in 2013, we performed hypervelocity impact shock analysis of a typical comet mixture containing ammonia, CO2, and methanol. And then we show you here a single ion GCMS trace, and we see several amino acids have been detected, namely glycine here on the bottom, D and L alanine, alpha IB, alpha ABA, and isovaline and DNL norvaline. So a large range of amino acids have been indeed generated. So this table summarizes what we found. We've placed a mixture, different mixtures. We've placed ammonia. So starting on the bottom, we placed ammonia with CO2. And this did not generate any amino acids. And then we put the right abundances. So we placed ammonia, CO2, and methanol with impact velocities that are very low. We knew it wouldn't generate any amino acids, and indeed it didn't. And then we have tested with the ab initio molecular dynamic simulations that we needed a minimum of 7 kilometers per second of impact velocity to generate amino acids. And experimentally we tested that, and we've seen that indeed, and it's the two top lines, that with the right ice mixture containing ammonia, CO2, and methanol, and the right impact velocity, a minimum of 7 kilometers per second, we indeed would detect amino acids. So this shows that the impact of comets and also the impact of meteorites into icy surfaces will produce alpha amino acid. And this is important not only for the origin of life on Earth, because it shows that comets may have played a key role on the origin of life on Earth, bringing the building blocks of life, but also for many other planetary bodies throughout our solar system. In this image, we see several planetary bodies, moons in this case, that have an icy surface. And so the impacts may have indeed generate organic molecules. So this is also important when we have future space missions to those bodies in our solar system. In conclusion, what I've tried to show you in this talk is that comets, asteroids, and meteorites, they are very rich in organic matter. They contain carbonaceous material, and this material was exogenous delivered to the early Earth. By analyzing the organic content of comets, asteroids, and meteorites, so we analyze meteorites in the laboratory, and we have several missions to comets and asteroids, present or future missions. This will provide us a window into the chemistry of the early solar system. And this is very important to try to understand how this organic matter was synthesized. In addition to this, we've also studied that hypervelocity impact shock of a typical comet ice mixture produce several alpha amino acids. So this is an additional way to synthesize organic matter that may be delivered exogenously to the early Earth and to other planetary bodies of our solar system. We've also showed you in this talk that all the key components that are important in terrestrial biochemistry have been identified as extraterrestrial molecules in carbonaceous meteorites. In terms of space missions, both in terms of past, present, and future space missions, through primitive celestial bodies such as comets and asteroids, they are crucial to understand the origin and evolution of organic matter in the solar system. So not only we need to analyze meteorites in the laboratory, very primitive meteorites in the laboratory, but for sure we need those space missions, even though they take several years to complete, but they are a key step in understanding the origin and evolution of organic matter in the solar system. So the analysis of all the organic content of comets, asteroids, and meteorites provide us a window into the resources that were available by the first living organisms on Earth, and on other places of our solar system where life could have potentially originated. And all this contributes to understand what's the exogenous contribution for the origin of life on Earth and potentially in other places of our solar system. Thank you.